And I was like, I just couldn't do it. That was right.
So just a minute to go. Hope you guys had a good long weekend. It's nice to get that off. A little early, I think, in the semester. I want a long weekend in October. Be nice. So I have started uploading some of the pencasts. I know some of you could not access the Google form. I think it wants to check if you're a registered Maricopa user. So I think you have to sign into your Maricopa account in order to access the form. Next time I'll just remove that security. There's an extra security that Maricopa places. I figured out how to do that. So I'll go ahead and remove it. So next time I think everybody should be able to access that, right? But it doesn't matter. I got enough responses. I started putting some pencasts. You'll find them in Chapter 1 module. It'll say Chapter 1 and 3 pencasts. And I'm working out some problems and things like that. So I'll add some more today. So you'll have that. And let me know, okay? So what we're going to do today is move on to the last portion of that Chapter 1 and 3 module, which is Chapter 3. Couple things here. One is functional groups, which is completely memorization. So we're going to start with that first. Just one little problem, because it's not going to be fun, because you obviously will not have it all memorized in a couple minutes. So you will work on that. And then second part is very straightforward. It's intermolecular forces. You've covered that in Gen Chem. So you might see me just going a little bit faster in this. And then we may have time, I think we will have time to get into Chapter 2, which is acids and bases, and we'll spend more time there. Not a difficult chapter, but a very important chapter. Okay, so I'll spend more time there. So we'll get started with functional groups. So we have millions and millions of organic molecules. It is almost impossible, just like your inorganic compounds or all the elements on the periodic table, it is impossible to study the properties of every compound. So typically what chemists do is categorize everything. So they've taken all the elements, put them in families, we call them groups, put them in a periodic table. So if we know a little bit about lithium, we can predict the properties of cesium and so on. So similarly with ionic compounds, you can divide them into different categories, you know, the binary ionic, ternary ionic, all that stuff. Similarly, in organic chemistry, we take compounds with similar physical and chemical properties, group them in families. These families are called functional groups. Functional groups form the basis for studying organic molecules. So the way you name a molecule is based on the functional group. So given a molecule, if you're asked to name it, by end of 1 year, you will be able to name most of the organic molecules known to man, because you will look for the functional group and you know the rules for naming those kind of compounds, so you'll be able to name that particular molecule. You can predict its physical properties, and what is really powerful about a functional group is you can predict all the chemical reactions that particular molecule undergoes. You can also extend it further. If you want to make a particular molecule, you want to synthesize something, you look for the functional group, and there are definite methodologies that you will use to make that particular molecule. So functional groups are extremely important. It is pure memorization, so short-term memory. So you want to look at it and keep looking at it on and off. You just get very straightforward questions. Given this molecule, name the functional groups. That's all it's going to be. Okay. So we will get started with what all it determines, the type and strength of intermolecular forces. So which in turn is going to affect its boiling point, melting point, refractive index, whatnot, bonding and shape, physical properties, how you name it, and all the chemical reactions. Okay. So this is the key thing. So let's look at this. So any compound that contains only carbon-carbon bonds and carbon-hydrogen bonds are called hydrocarbons. So hydrocarbons, from the name you can see, it contains only two elements, carbon and hydrogen. So two kinds of bonds you're going to find in that. One is carbon-carbon bonds, carbon-hydrogen bonds. But at this point, you know, you can have, don't worry about the valency of carbon. I'm just being really quick here. So you can have single bonded, double bonded, and triple bonded carbon, and then you have, of course, carbon, hydrogen. They all fall under the category of hydrocarbons. There are 4 major types of hydrocarbons. If your compound contains only carbon-carbon single bonds and carbon-hydrogen bonds, so here I'm only talking about carbon-carbon single bonds, then it's called an alkane. All organic molecules will contain carbon-carbon single bonds and carbon-hydrogen single bonds. So all organic molecules can technically be called an alkane. So you will identify a functional group as an alkane only if you do not have any other functional group present. Got it? So you're not going to call every organic molecule an alkane because every organic molecule will have those types of bonds. So the type of compound and the functional group are interchangeable, although Smith places them in 2 separate columns. Alkane is anything that contains carbon-carbon single bonds and carbon-hydrogen bonds. If you have carbon double bonded to carbon, it's called an alkene. The functional group is a double bond, but you can certainly call the functional group alkene. No harm with that. So these 2 are pretty interchangeable. Okay. What this means is if you take an alkene, the reaction is going to occur right at the double bond. That's where the reactions are going to occur. The geometry, the properties, all of them depend on that double bond. Triple bonded compounds are called alkynes. So I have some little pictures there. Alkane is a fuel that goes into your car. Alkenes are very common ingredients, main constituents of lemons, citrus fruits, basically. Alkyne, it's the main pharmaceutical in the birth control pills. Aromatic compound, you have a 6-membered ring with alternating single and double bonds. At this point, I want to tell you that you can draw them rotated inside the other way. It does not matter. So what you're really doing is a resonance. So at this point, you know what a resonance means. So you can use that to rotate those pi bonds inside the ring. So you can call that functional group phenyl group, aromatic compound. Some textbooks will call it arene. Means the same thing. Okay. So main constituent of a number of compounds, one that is shown there is a cigarette smoke. Also a main constituent if you barbecue food. Anytime food chars, turns black, you have that. Okay. Next we have a series that contains the heteroatoms. Alkyl halides, main constituents of pesticides and also the refrigerants, the freon that goes in your fridge, contains alkyl halides. They're big pollutants in the atmosphere, so they're being slowly phased out, but the carbon-halogen bond there is very important. So it can be any halogen there. It's called the halo group. As I said, these are interchangeable. The important thing there is that carbon is sp3 hybridized. Alcohol contains what is famously in inorganic chemistry called the hydroxide. This is called the hydroxide, but you'll no longer call it the hydroxide. You'll call it the hydroxy or the hydroxyl. So you can add an L to that. That's because the hydroxide is an ionic bond, whereas the hydroxyl is a covalent bond. So you cannot use hydroxide in organic. Okay. So when you have that hydroxy group connected, that is an alcohol, and this is again sp3 hybridized. Then we have the ethers. So what you see there is the mint leaves contains alcohols. So a number of compounds contain alcohols. Ethers are very useful in the field of medicine as anesthetics. Oxygen is flanked on both sides by an alkyl group or an R group, or in organic chemistry stands for rest of the molecule. So you can have anything. This is very simple. All you have is a CH3 group, which is called an alkyl group. But basically, it's the rest of the molecule. The key thing is oxygen is flanked on both sides by carbon. These carbons can be sp3, sp2, or sp hybridized. You can have a whole variety there. Then we have the amines. The amines are main constituents in fish. So decaying fish has the classic odor that comes from the amines. Okay, so they don't smell good. Amines smell really bad. And nitrogen is connected to a carbon. That carbon is sp3 hybridized. There are 3 kinds of amines. If the nitrogen is connected to one carbon, like the example shown here, it is called a primary amine. Primary in organic chemistry is indicated as 1 degree. but you don't read it as 1 degree, you read it as primary. If the nitrogen is connected to 2 carbons, so I'm going to connect it to 2 carbons now. This is called a secondary amine. And if it's connected to 3 carbons, it's called a tertiary amine. To get started with, you want to learn amines, and then you can add more to that once you start looking at the primary, secondary, and tertiary a lot more this semester. Okay. The thiol is very similar to the alcohol. Take a look at the thiol and compare it to the alcohol. All you're doing is you're replacing the oxygen with the sulfur. So the thiol is a sulfur analog of the alcohol. The sulfide is very similar to the ether. It's a sulfur analog of the ether. You're replacing the oxygen with the sulfur. Okay? So those are the next series of functional groups. So what you want to do is get a flashcard, right? Get this name, alkyl halide, get this structure. It's up to you if you want to get an example or not. Okay? So maybe you want to get the name on one side and then you want to get the general structure on the back side. Maybe your example will go right below the general structure. You want to quiz yourself. Okay? You either know it or you don't. So it's just memorization.
I have a question.
Yes.
Is it very important that we know the hybridization for each of those?
No, it's not very important. What I'm saying is if the nitrogen is connected to sp3, it's called amine. If it's connected to sp2, it's called imine, but imine is not one of them on the list. So I'm just giving you that detail there. That's all. In other words, if you forgot the detail, you'll probably still identify it as the amine. You will not have the imine. So answer is yes and no. But you need to know that it's an amine. That's really key. Then we have a series of groups which contain the C double bond O. The C double bond O is called the carbonyl. It's one of the very important groups in organic chemistry, and we have a number of them there. So the first one is the aldehyde. There are some minor differences, and we want to look at that. The aldehyde, all of them contain the C double bond O. So this carbon right here is called the carbonyl carbon. Again, one side, it can be very complex, very simple, whatever. But aldehyde has a hydrogen directly connected to the carbonyl carbon. That's how you identify an aldehyde. What you see there is cinnamon, cinnamaldehyde. So aldehydes are found in a number of natural products as well. So key thing for an aldehyde is hydrogen directly connected to a carbonyl carbon. Ketone, you don't have any hydrogen directly connected to the carbonyl carbon. It's flanked on both sides by carbons. Those carbons can be sp3, sp2, they can be aromatic, sp, whatever. Okay, doesn't matter, but no hydrogens. So carboxylic acid, ibuprofen contains this carboxylic acid. You have what is called the hydroxyl group. We just got introduced to that. So the alcohol group directly connected to the carbonyl carbon is called a carboxylic acid. If you get this as part of the molecule, you're not going to identify it as two functional groups. I don't want you to identify it as carbonyl and alcohol, but what you need to do is identify this entire group as carboxylic acid. Okay? Although I'm breaking it apart and teaching you that way, that entire group should be identified. Then we have the ester group. The ester group contains an sort of like an ether. You have oxygen flanked both sides by carbon, but one side the carbon is the carbonyl carbon. Ester is commonly confused with ether. They are different. Ether, you have both sides carbon, whereas ester, one side is a C double bond O. All right. The other side can be the rest of the molecule again, something else. Amide, commonly confused with amine. Those are different. Amine, you have the NH2 connected to the rest of the molecule. But here, you can have the NH2 again, but it's connected on one side to the carbonyl. Okay. Again, the nitrogen can be connected to one carbon, two carbons, or three carbons. So you can have the primary, secondary, and the tertiary amides. But again, I'll start out simple, start with the amide, and then you can build in more. When I say that building into the primary, secondary, and tertiary will start with the second exam. Okay, So the first exam, if you just identify it as an amide, amine, you're good to go. And then you can add more to it. So any questions here? So I don't know how well this is going to happen. Maybe I'm the only one who's going to answer it. But here is a molecule. This is a typical question. You can get this. The structures are going to be really complex. Don't worry about it. Our goal is to identify the different functional groups that we see here. Okay? So we'll get started. Maybe I'll ask you. If I don't get the answer, I'll write it. I know you just got a whole lot of information. So you can either do that or you can have a circle around it. That's up to you on the exam. If it's a free response question, you can circle it, have an arrow, or just have an arrow. So that one, what is that? Yeah, so you can call it aromatic compound. Some of it will call it maybe phenyl ring, that is fine, or arene. So Smith uses this as well. So you don't have to write everything, just write any one. Okay, so you do see that here, you do see that here, right? They're all the same. Okay, let's go here. And we have one here. Very good. These are alcohols. And then what about this? Very good. Carboxylic acid. Right. Then let's look at this. Yeah, this is the amide. Okay. Then let's look at these double bonds. What are those? So double bonds are called alkenes. Okay. So we're going to write alkene. So I think that's about it. There is one here, but it's not on the list. Okay, your alkyl halides. Remember I gave you the detail, is usually sp3. That is sp3. So this is not an alkyl halide. This carbon is not sp3. That is definitely a functional group. It is not an alkyl halide. If you're just curious, it's called an aryl halide. What that means is an alkyl halide and an aryl halide will not show the same chemical reactivity. They will not be named the same way. Their bonding and structure will be different. Okay, that's what it means. When the functional groups are different, that's what it is. So I do have some extra problems in Canvas, which contains a lot of these big molecules. You're asked to identify functional groups. That's the question. There's nothing else about it on these slides. Okay, do you have anything here? So we're going to go into a topic that's very familiar to you. I don't think, when cruise through this, I don't think it's going to be a major issue, but it'll probably serve as a good review. We have intermolecular forces. So there is a difference between intermolecular forces and intramolecular forces. What is the difference? Intramolecular and intermolecular. So I have, let's say, a molecule here. I have one here, here. What is intermolecular? So there's a force of attraction between the molecules, that is intermolecular. What is intramolecular? That's within the molecule, right? So what is that called? Yeah, that for us is covalent bonding, okay? So intramolecular, what holds within the molecule is what's holding the atoms. You have ionic bonding, coordinate bonding, all that. But for us, it's covalent bonding. So we're not talking about what's within the molecule. We're talking about what's between the molecule. There are different kinds of intermolecular forces. One of them is called the ion-ion interaction, which you know really well. So if you have sodium and chloride, you know that, you know the structure really well. It takes on a cubic lattice, right? And then you have the sodium surrounded by the chloride and vice versa. And what's holding, you really don't represent sodium chloride like that. This line is not correct. It's used only for covalent bonding, okay? So this is not a correct representation. This is how you would represent sodium chloride. So you have a strong intermolecular, because you have discrete units of sodium ion and chloride ion. So between the sodium ion and chloride ion, you have the strong ionic force of attraction. So that is the one that you're really familiar with, but these I'm sure you have covered. These are called van der Waals forces. They have a couple other names. What are those? Very good. London forces, dispersion forces means the same. Okay. So if you take a very non-polar molecule, what is shown there is methane. So you can see the carbon right there and then 4 hydrogens. Right. These bonds are essentially non-polar. So you really don't have a delta plus, delta minus on any of these atoms. But you can see that one of the spheres, one side of the sphere takes on a delta plus. When it comes close to another methane molecule, you have a delta minus. So even in non-polar molecules, you can have an unsymmetrical distribution of electrons. Why is that? So the bonds are essentially non-polar. So I don't think there's a reason for electrons to move to one side of the molecule more than the other. But this can happen in all molecules. So what is the reason for London forces? It rotates, and what happens is in space, these are not static and we are not living in vacuum. We are surrounded by electrical and magnetic fields. Constantly there is some electricity going through, and our Earth itself is a big magnet. Okay, so when these molecules, they are just rotating, orienting themselves in space randomly, what happens is there's some electrical and magnetic disturbances. So it's very fleeting. So for a fleeting second or even less, there can be an unsymmetrical distribution of electrons, because maybe electrons are attracted to one side of the magnetic pole a little bit more than the other. Okay, so that's when this happens. So it's very temporary. It's not like a permanent dipole. That's why van der Waals forces are very weak, but they occur in all types of molecules. Polar, non-polar, it doesn't matter, because you can always have these disturbances. So that's what's going to attract a couple of these non-polar molecules next to each other. Okay, so that kind of force is called a van der Waals force. So let's look at how it's going to affect some of the properties in organic molecules. I have two structures here. I have pentane on the left. I have neopentane on the right. They both contain the same number of carbon atoms. One is a long molecule. The other one, of course, is a compact molecule. The question is which one will have more van der Waals force. So the idea is the bigger the surface area, you're going to spread the charge out more. Okay, so you're going to have a greater spreading of the charge. So you're going to have greater intermolecular force there, which we're talking about right now is the van der Waals force. More compact, you don't have that much of surface area. So van der Waals force is dependent on surface area. Larger the surface area, stronger is the van der Waals force. So why is this a big deal? So if you have really strong force of attraction between two molecules, and let's say this is a gas, but let's say it's a solid and you want to melt it, you have to go in and break that and push those molecules away. Because going from a solid to liquid, you're pushing the molecules further away. Liquid to gas, completely far away, right? So it all depends on how strong the intermolecular force of attraction is. Depending on that, you'll have to work harder. If it's stronger, you have to work harder. The melting points and boiling points will go up. So the key thing here is larger the surface area, stronger the van der Waals. Okay. So let's take a look at a couple things here. No new information on the top portion of the slide. We have 3-pentanone and acetone. They both fall in the same functional group. Maybe it's a little early for this question, but what kind of functional group is this? The only reason I'm asking you is every time you look at a molecule, just quiz yourself what kind of functional group. Okay, so this one is carbonyl. Everybody sees that? C double bond O right there. Both sides, you have carbon, no hydrogen directly connected to the carbonyl. So these two are ketones. So ketone is the functional group. So they both have the same functional group, but I want you to look at the boiling points. One is much larger than the other, because one is a larger molecule, you have greater surface area, the other one is less. Okay, so this example is just to show that groups that have molecules that have the same functional group can have extremely different boiling and melting points. Okay, you can predict some of it, but it does depend on the surface area. The bottom one may or may not be new information, but there is a new term, polarizability. So let's see what that means. So here these two pictures will come in very handy. Again, you have the same type of functional group. I have a halogen, connected to a carbon, this carbon is sp3 hybridized in each case. Okay, so this functional group is an alkyl halide. In one case, I have iodine, the other case, I have fluorine. Okay, so I want you to focus on this bond here. Which bond is longer, carbon iodine or carbon fluorine? Carbon iodine bond is a much longer bond. Why? So, which is a strong? You can answer this question in many ways. The point is, which one is more electronegative, fluorine or iodine? Fluorine. But you want to look at the periodic table. They are going down a group. Remember I told you this? Electronegativity is not an effect here. What is? Size. So iodine is a much bigger atom. So that's why that overlap, that carbon-iodine bond overlap is not strong. You got a little carbon, you got a big iodine. You're not going to have a strong overlap. Therefore, you're going to have a weak bond. Once you have a weak bond, the bond length increases. Because you don't have a good overlap. Those atoms are not coming in proximity to give you a strong bond, which means they are a little bit further out, right? So that makes a carbon-iodine bond really long. So when an atom is just moving away from the other atom, it's not as close as it needs to be, it's moving further away, the electrons of the iodine are not going to be shared very well by carbon. So they're going to spread out. You're going to have greater spreading out of the electrons from the iodine. This spreading of electrons is called polarizability. So it's just, that's the new term for you, okay? So iodine is more polarizable than fluorine. Why? Because iodine is much larger. The overlap with the carbon is not that strong. So iodine has moved further away from the carbon atom. So the electrons in the iodine are just spreading out. There's nothing to hold it so tightly. Okay? In that covalent bond, the valence electrons of the iodine need to be held tightly, but it's not going to be. So look at the boiling points on those. More polarizable has a higher boiling point. Minus 78 is a lower boiling point. So when it's more polarizable, the atom spreads more. So, the electrons spread more, right? So you have greater surface area. Everybody clear with that? So more polarizable, more surface area, higher van der Waals force, higher boiling point. I'll ask you not a related question, but between the two, which one do you think is more reactive? Carbon iodine, can you break that more easily, or the carbon fluoride? The carbon iodine can be broken more easily. See, that bond is already lengthened out. Okay, so you can go ahead and break it more easily. Okay, so you'll have to use theories differently to explain what you observe. But electronegativity is not going to play a role here. That's the key thing. Okay, anything you want me to explain there? So polarizability is a size effect. Larger the size of the atom, more the spreading of the charge, more polarizable that particular atom is. In this context, the more polarizable, greater is the surface area, greater is the van der Waals force. Okay, that's kind of how we are explaining what we observe. So larger the surface area, higher the boiling point. Same with the melting point. More polarizable, higher the melting and boiling points. So that completes the van der Waals discussion. Next we move on to dipole-dipole. So this is different from van der Waals in some ways. Van der Waals is still delta plus, delta minus. This is still the same, but this is a permanent dipole. This results because of electronegativity. There's a difference, there's a distinct difference in electronegativity. So one atom is always going to love electrons more than the other. So there will be an unequal spreading of electrons in that unsymmetrical, sharing of electrons in the covalent bond that creates this dipole. In this case, you pretty much know this. Oxygen is delta minus, carbon is delta plus. I'm ignoring the other bonds. They're essentially nonpolar. So what happens is these will orient in space such that an oxygen will see the carbonyl. So it'll always be like this. Okay, that's kind of the orientation you're going to see. And that is your dipole-dipole interaction. You can also simply call it the dipole force, but this is permanent. So its effect on the physical and chemical properties will be a lot greater than the van der Waals force. The last one that you know very well is hydrogen bonding. How do you define a hydrogen bond? It's a bond between hydrogen and three key elements. Which ones? Very good. Nitrogen, oxygen, and fluorine. So those three, the most electronegative elements are what we are looking at. So this is again a polar covalent bond, sort of, right? But it is intramolecular. It is still a dipole force, because I can certainly go ahead and say delta minus here and delta plus here. So the hydrogen bond is essentially a dipole force. However, it's different from something like this. The difference being, the difference in electronegativity between oxygen and hydrogen is much greater than oxygen and carbon, okay? So that's what makes it a much stronger intramolecular force. Is everyone clear with that? Hydrogen bond is still a dipole force, but we give it a different name, we categorize it differently. We don't include the hydrogen bond under the same category as dipole force. That's because if you replace it with nitrogen or with fluorine, that difference in electronegativity between hydrogen and those electronegative elements is much greater than the difference between carbon and oxygen, nitrogen and oxygen, okay? Because those are much closer on the periodic table. You're not going to see that great a difference in electronegativity. So hydrogen bonding is a much stronger intermolecular force of attraction compared to a dipole force. You have learned a lot more about hydrogen bonding. You know that's the reason why ice floats on water. You know that's the reason why DNA is a double helix, the strands don't separate, okay? And that's the reason why Watson and Crick won their Nobel Prize. They could apply the hydrogen bonding to the structure of DNA. So you must have covered a lot of this in Gen Chem. So it's just a summary table here. Van der Waals, very weak. Okay, that's all molecules. So example is a very non-polar molecule and a very polar molecule right there. It's there in everything. Dipole, dipole, you got to have some polarity, which means you got to have polar covalent bonds. So you got to have a polar covalent bond such as a CO bond, again a CO bond, OH bond. You got to have some polar bonds. Hydrogen bond, you're specifically looking for these bonds. Okay, ionic bond, we're not going to see that much at all for a very long time, because we are not going to combine our organic with metals for a long time. So once we get there, we can talk more about that. That just gives you a summary table. I think you should be doing fine, right? You've seen this before. Again, just some summary slides coming here. Increasing strength of intermolecular forces, boiling point is going to increase. Okay, so compounds with hydrogen bonding will always have much higher boiling point than those with dipole forces compared to van der Waals. So if you take a look at this example and you're asked arrange them, we'll do some problems, but you're asked to arrange them in the order of increasing intermolecular forces, you must remember that all of them contain van der Waals force. So that's kind of how your analysis should be. Pentane contains only that. Butanol, you don't have to really waste your time drawing a structure, but you should be able to see that you have a carbon-oxygen bond. So this contains a dipole force as well. Here you do have a carbon-oxygen bond and an oxygen-hydrogen bond. So you do have dipole force there as well. But this one specifically has hydrogen bonding, right? Because you have that oxygen-hydrogen bond. When you have hydrogen connected to oxygen, nitrogen, and fluorine, that is a special kind of bond. So more number of intramolecular forces, higher will be the boiling point. And that's kind of, your analysis is going to go that way, your thought process. So stop me if you have any questions, or I just keep scrolling.
For the second structure, I see hydrogen bond.
Now what you see is this. Yeah. It looks like these are connected, but they're not. Yeah. So take a minute here. In each pair, you're going to say which one has a higher boiling point and explain your choice. Questions are not going to be any more complicated than this. It's just as straightforward as these are, okay? So what I would do is take the first one there. So I'm going to work on the first molecule in the pair. That one contains van der Waals force. The next one, well, all molecules contain that. Then this one, you should clearly see a carbon-oxygen bond, which means you have a dipole force. Right there, you should see a carbon-oxygen, oxygen-hydrogen bond has a dipole force. But right there, you see that hydroxyl group, okay? That is hydrogen bonding. So this one is going to be the higher boiling point. Explain your choice, just has more number of intramolecular forces, right? Fairly straightforward. Next one, B. Both of them are nonpolar compounds. The first one has 4 carbons. The next one has 5 carbons. So they're straight chain. They're not branched or anything. There's no compact arrangement here. So this one is going to have a higher surface area and therefore will have higher boiling point. Okay? Anything? Good. Okay, let's look at melting points. Not very different from boiling, but there's a slight tricky thing here that I want to focus on. Again, nothing major with this slide. Again, more number of intramolecular forces, higher the melting point. So I don't think that's an issue. So when you look at this example, it should all fit in. Pentane has only van der Waals forces. Look at the melting point, minus 130, whereas 1-butanol has all 3 kinds of intramolecular forces, van der Waals, dipole, and hydrogen bonding. So that's minus 90, which is higher, okay? No major, deviation from what we learned. But here is the exception or the deviation that we need to watch for with the melting point. If you take isopentane, that's minus 160. If you take neopentane, that is minus 17. When you look at these 2 molecules, this is almost a little bit, the one on the left almost feels like a little bit more surface area than the right, okay? Because you have a little bit of a longer chain here. That's kind of how I'm thinking at least, right? But this one's a much shorter chain. So I'm thinking not much of a surface area in the neopentane. But you can see that minus 17 is a much higher melting point than minus 160. So with the solids, the more symmetrical, the more compact the arrangement, stronger is the packing in the solid. So here that's a new thing. Higher the symmetry, higher the melting point. The thing with the solids is they're not just on their own. They are usually in a crystal lattice. And the lattice has many structures, space-centered cube, body-centered cube. You have studied a lot of that, right? So there is some very ordered packing in solids. So when you want to melt this, make it a liquid, you're bringing some disorder, which means you need to go in and break it. When these little circles are more compact and more symmetrical, you can have a better packing, which makes your melting process a little bit more difficult. What I mean by that is you have to spend more time, more energy breaking it. We don't have that in the boiling point situation because you're going from disorder to greater disorder, liquid to gas. But solid to liquid, you're going from great, degree of order to some much higher disorder. That's the thing. You want to remember that for the melting points, okay? So more symmetry, higher the melting point. We didn't have that in the boiling point. Our next property is solubility. So we have different kinds of solvents. At this point, I'll say we have 2 major kinds of solvents. We have polar solvents like water, and then we have non-polar solvents like carbon tetrachloride. CCl4 does have polar bonds, but essentially the molecule is non-polar. Why is that? So what's the shape of that? And it'll cancel it out. Okay, so that is a non-polar molecule. If you take butane, it is non-polar. So like dissolves like, you can see how it dissolves in CCl4 but not in water. You take acetone, you got the polarity right there. Delta minus on the oxygen, delta plus on the carbon. Okay, this is no big deal. It is soluble in water, like dissolves like. But this is a little bit of a surprise. It is soluble in CCl4, and why is that?
Same shape.
Think about those. So what kind of bonds are those? Carbon-hydrogen bonds. Polar or non-polar? How many of those do you have? 6 carbon-hydrogen non-polar bonds. The non-polar portion of the molecule is responsible for acetone to be soluble in CCl4. Okay, so the organic compounds can be soluble in both. So like dissolves like works okay. You only have one polar bonds. Only one polar bond, that is a C double bond O bond. That's what is responsible for it to be soluble in water. But then you have a whole lot of non-polar carbon-hydrogen bonds. That's what makes it soluble in CCl4. Okay, so you have to watch for the entire molecule when you predict solubility. Here is a comparison. You have 2 molecules, same functional group. Do you want to guess the functional group? Yeah, they are alcohols. So where is it? Right here, right? See that? That's where the functional group is. But one is water soluble, that's ethanol. The other one, cholesterol, is not water soluble. Okay, you do have this, and you expect that group to hydrogen bond with water. However, you have a big portion of the molecule that is completely non-polar, and that is not going to make it soluble in water. Okay, so you can't just focus only on that functional group. For solubility, you have to look at the entire molecule and make a decision. So which of the following are predicted to be water soluble? First one. So you have that hydroxyl group. Okay, so yes, it is water soluble. You have this, which can make it water soluble, but this one is maybe sparingly soluble. Okay, you're not very sure by looking at this structure that this does take a delta minus and delta plus, but the polarity difference may not be great enough to get it to solubilize in water. For something to be soluble in water, you really want hydrogen bonding, and that is not going to be possible here. So maybe a little bit of it will dissolve. If you want to say that's insoluble, that is fine. Okay? Everybody okay with this concept? So the last slide here, take a few minutes. You're going to identify all the letters. What you're going to say, identify is the intramolecular forces labeled A through F. So that is the structure of a protein. I'm sorry?
If a molecule is polar, it is also soluble in water.
If it is polar, it will be soluble in water, but it depends on, it's not safe to say that, because your polarity is based on certain segments of the molecule. Those sections, it can be polar, but if it has a very big hydrocarbon section, it may not be soluble.
How big is it? Like how many carbons is so
I think you're looking at something like 9 and higher. There's a cutoff value for that, yeah.
There was a rule that we learned that was the greater than 5 carbon rule. Is that applied?
Yeah, you can apply that one too.
Okay.
Yeah. That's right. Typically, 2 extremes are compared, like that little alcohol with the cholesterol, and you really don't even have to apply the rule, but that rule will work, definitely. When the hydrocarbon chain is very big, you're not going to be able to get it to soluble.
The part that's polar is too small to overcome.
Yes, that's right.
Okay.
That is the principle, yeah.
Thank you.
So the first one, what is this? So that is van der Waals. Okay, what about B? Yeah, this can be hydrogen bonding. If you write dipole force, you're right, but that is really hydrogen bonding. And this one again, when you have the NH2, you have hydrogen bonding right there. This one, C. So this is ionic because you have a definite charge, plus and minus, okay? For dipole, go with delta plus, delta minus. That's a convention. When you have a full plus and full minus, it's an ionic bond. This one is a definite case of hydrogen bonding, right? Very good with that. And F is again a van der Waals force. Right. So that's about it for chapter 3. I did move a little faster here, so I thought we could use the time to spend more time on a little bit more difficult topic that comes up. Let me get this open. Acids and bases, because this is where you start learning how to predict products and how to draw arrows, and that's a little bit of an uphill climb, and that's there for exam 1. So, but if you feel I've gone too fast and you want me to focus on something, let me know. Okay, take a look at chapter 3. Let me know. But typically it's smooth sailing 1. Okay, but let me know if you have any questions. But what I want to do is move on to chapter 2. But before I do that, anything about chapter 3, functional groups. Okay, so we look at acids and bases, and as I mentioned in the syllabus, I'm not going to focus on the Bronsted-Lowry. I have like one slide on it, and that's it. We'll focus heavily on our own definitions in this discipline, which are the Lewis acid and base definitions. So let's take a look at the structure of morphine. What we have is very typical of organic molecules, unlike inorganic molecules where you're given a particular molecule, it's an acid, another one is exclusively a base, hydrochloric acid, sodium hydroxide, and then you have some that can function as acid and base. But here you have many sites that some of them are acidic, some of them are basic. So let's look at the acidic sites. Again, boils down to polarity, okay? So I'm going to put the delta minus on the oxygen, delta plus on the hydrogen. So a base can come, grab this hydrogen, which means the base is attacking the nucleus of the hydrogen. It's grabbing the proton. So which makes these two alcohols proton donors, and therefore they are acids. Make sense? Okay. Base. So base sites are those that can attack something that's positively charged. For us, a common one is a proton. So there's a pi bond which can go attack that. Here is a lone pair that can attack the proton. So those are our basic sites. So within a molecule, you can have acidic as well as basic sites. So we need to know what we are going to add, what attacks what site. That's kind of the idea. So just to show you that we can have both kinds of acidic and basic parts in the same molecule, that's what is the goal of this slide. This is a quick rundown. You know this really well. All I need you to know is higher the Ka, right? Stronger is the acid. So that's the big thing that I want you to know here, okay? So that is really important for us. We do not use the pH scale. It's not broad enough. So we use the pKa scale. It's much wider range, and that's the reason we're going with that. I won't ask you any calculations or anything of that sort. So let's do a quick rundown. It's very quick, one semester of acids and bases on one slide. Which is a stronger acid? Okay, 5.2. Okay, lower the pK, stronger the acid. Which one is the stronger acid? Now we're talking about the acid dissociation constant, which is the Ka. Okay, -3. I'm just going to assume you don't want to talk to me, but you know this, right? Okay, so on the next one, for each of the compounds, you're going to write the form that predominates in a solution, which means I'm going to take a beaker, I'm going to fill it with the solution, and the pH for that solution is 5.5. So I'm going to throw each of these compounds, not all 3 into the same beaker, okay? One after the other in 3 different beakers. So I'm going to throw the acetic acid, whatever, you know, This is acetic acid. You don't have to know the name, but its pK is 4.76. I'm going to throw it in a beaker with a pH 5.5. So which is the stronger acid here, 4.76 or 5.55? 4.76, which makes 5.5 function as a base. So the predominant form here will be CH3. I'm going to open this up. Okay, that's how that looks. So the 5.5 is going to come. I don't know what that is, but it's going to come. Grab this proton. Proton is H plus. And it's going to drop that sigma bond on it. So the predominant one will be CH3, C double bond O, starts with 2 lone pairs of electrons. That sigma bond is going to form the third lone pair, negative charge. All right? That's what it is. That's the predominant form. Any questions? Let's look at 11.0. 11.0, 5.5. Who's the stronger acid here? 5.5. So the 11.0 is going to function as a base, right? The 5.5 is a stronger acid. So the base, this is not going to give up your proton. That's what's going to happen. All right? So the predominant form for this can be left as such. You don't know the structure of the 5.5. You can leave it as such. 9.4 and 5.5. So stronger acid is 5.5. So 9.4 is going to stay as such, NH4 plus. Okay, it's not going to give up its proton to a stronger acid. So you can leave the predominant form as such. So it depends. The point here is a compound can function as an acid or base depending on what the other compound is. It's all relative. Tiffany?
So that ends up being the conjugate on the right side that you drew up there.
Yeah, this would be the answer for this one.
So that's a conjugate bit, or
That's a conjugate base. That's correct. So if this is the acid, that's going to accept a proton to become that, so it's a conjugate base.
So are you assuming that the pK is the actual value of the pH? So you're giving it a pH.
It's not, but that's how the comparison is done. We don't have a calculation. We're not going to do a calculation to convert the pK into pH. We're just going to compare it directly.
So you're just going to assume that they're close enough in value that you can. Okay.
Right.
So I was like, how are you guys getting these?
Yeah, you're not going to make it. You can compare them directly.
Okay.
Then it's an approximation, but it works.
Okay. Good.
Because they're so, they're so separated. It doesn't matter. I know. Yeah. It's not an exact calculation. If we're not going to invoke that.
But
Just qualitatively, it works fine.
Okay.
Yeah.
So it's okay to compare.
So this is where I want to spend some time with you, where this is a skill that you need to build. So that's all I'm talking about Bronsted-Lowry, hardly anything. Okay, so we are going to work more on our own terminology. So this first question, we are going to learn to draw products of the acid-base reaction. Everybody knows this is a base. Okay, so I'm going to start with what we know so well, that is sodium hydroxide. When you see a metal, it's an ionic bond. So break it down, write that hydroxide like that. I want you to get a little bit more detail there. Oxygen has 2 lone pairs. When it has a negative charge, that negative charge indicates an extra lone pair. So I want you to draw hydroxide like that. Okay, because we are going to get into showing how electrons move. Then what I want you to do, I don't want to draw the full structure here. So I'm just going to go ahead and pull just this section here. Okay. I'm not looking at the rest of the structure. The reason being, the most polar bond in this molecule is the oxygen-hydrogen bond. Do you all agree with me? That's where the greatest difference in electronegativity is when you look at the periodic table. So rest of it, I'm just going to say or, rest of the molecule. You can certainly do that on the exam. If you're given such a complex molecule, don't spend time writing all that. You can just say something like this is equal to or and just continue. Now I'm going to place the 2 lone pairs on that oxygen. You can certainly place the lone pairs on the double bonded oxygen, but I'm not going to do that unless I feel like I'm going to use that. This is delta minus, this is delta plus. Now I'm going to get the hydroxide here. You're going to draw what are called curved arrows. The curved arrows always start at an electron-rich site and end at an electron-poor site, which means you can start at a negative charge, end at a positive charge. You can start at a delta minus, you can end it at a delta plus. You can also go crisscross, okay? You can start at a delta minus and end on a positive. It's okay. It doesn't have to be delta delta. It doesn't have to be like that. So I'm going to start my arrow from one of the lone pairs, drop it on the hydrogen. I'm going to label this arrow 1. That's for my teaching purposes. You don't have to label that. What you should not do is this. I don't want you to start the arrow from the atom to the hydrogen. This is not allowed. Those curved arrows show the movement of electrons. If you start it from the atom, you're saying that the nucleus of the atom moves. All right? So you really need to start it from that electron pair and see where it ends. It ends on the symbol on the hydrogen, which means the lone pair attacks the nucleus of the hydrogen atom. That's what it means. This arrow 1 shows a bond formation between oxygen and hydrogen. Hydrogen has already formed a bond with the oxygen in the original molecule. Arrow 1 shows bond formation, which means you're forming an extra bond to the hydrogen. Hydrogen can form only one bond, which means you need to break a bond. So we're going to break the sigma bond. You need to drop it directly on the oxygen atom. That is your arrow 2. Arrow 2 indicates bond breaking, as a result of which, if you follow your arrows, oxygen had 2 lone pairs. The sigma bond now becomes a lone pair. The formal charge on the oxygen is now minus, and the other side becomes water. That oxygen which had 3 lone pairs will now have only 2 lone pairs, because one of its lone pairs has now formed a sigma bond. Okay? So this is called electron pushing arrow, also known as curved arrows. We use it a lot to show movement of electrons and to predict products. We build on this and then you start doing like 10 steps, but this is like a 1 step. That's kind of where we get started. Okay?
Where did the nitrogen or sodium go?
Yeah, so sodium is called a spectator ion. It's not really involved in the reaction. Sodium was hanging close to the hydroxide. Now sodium cannot hang close to the water because it's actually positively charged. So what it does is it comes and hangs close to this O minus. So you can stick it in right next to it. If you leave it out, it's not a big error, but that would be the completeness of it. So I know that's really bothersome in this class, but yes, that's what it does. That's it. You don't draw this because it's not an ionic bond. I mean, it's not a covalent bond. This force of attraction right here is ionic, so you leave it like that. You just stick it close to that. And it's exactly what you said. It floats around. It's spectator. It's not going to do anything else. Okay, I'll give you some time here. Try this one out. You got many polar bonds here that can throw you off a little bit. So we have a carbon-fluorine bond, we have a carbon-oxygen bond, we have a carbon-nitrogen bond, but the one we know really well is this acid. And you can certainly break this down completely and write it like that because you know it's a strong acid, but it is a covalent bond. If you want to write it like this, that is also acceptable with the chlorine, with the delta minus, hydrogen, delta plus. That is your choice. But that is our acid, which automatically makes the other molecule our base. But the question is, which part of the molecule is going to react? Okay, something needs to attack the H+. Certainly, your fluorines have a whole bunch of electrons. But there's something about the halogens that you should remember. They want to keep the electrons all to themselves because they're extremely electronegative. They're never going to donate their electrons to anything unless there's a convincing reason. You're not going to invoke the theory of halogens donating the electrons. So those guys are out. They are not going to give their electrons to attack the proton. That leaves us with oxygen with 2 lone pairs, nitrogen with 1 lone pair. We have oxygen and nitrogen on the same row. So what's the theory? Electronegativity or size? Electronegativity. Between the two, who is more fond of electrons? Oxygen. Who is more basic? No, answer carefully. Your first answer was correct. Who is more electronegative? Oxygen. Who is more basic? Who will give their lone pair more readily? Nitrogen. Nitrogen is more basic than oxygen. Something that's very electronegative is not going to donate its lone pair. You have to give your lone pair to attack the proton. You have to form a bond between yourself and the proton. Where's the bond going to come from? Someone needs to donate a lone pair. Oxygen is not going to do it. Nitrogen will, relatively. Nitrogen is the one that's going to be involved in the reaction. Couple of choices. You can attack that directly on the proton, but if you're invoking the covalent bond, you will attack it on the hydrogen. That will be arrow 1. This will be arrow 2. It's just a student preference. I've seen both. But that if you're just going to attack it on the proton, you do not have an arrow 2. So as a result of this, we'll call all of this R, N, H, CH3. And now it's attached itself to a hydrogen. Nitrogen will get a positive charge. Your Cl minus hangs close. So there's a huge difference in this discipline where we show electron movement. We do not do that in our earlier discipline where you simply predict products. Here we have to account for every electron, where it goes, whatnot. So everybody okay so far? So a couple problems there. Yeah.
Did that turn into an amine or an amine? Is that what that is?
This is, yeah, if you really, get into the details of it, this is called a quaternary amine. But that's what that is.
How did nitrogen become positive?
Yeah, because it formed an extra bond with the hydrogen that came from HCl. So now it has 4 bonds. It is not a normal bonding mode, right? 3 bonds and a lone pair is a normal bonding mode. So you'll have to calculate the formal charge gets a positive. Okay. So we go on to this table. We'll talk about it and then we are going to go into a series of slides. I don't think that much today, but Monday where we'll be working out problems, applying this single table, you'll have many problems, okay? So first one is the element effect, which is always, we're going to look across a period, down a group. So we have hydrogens connected to carbon, nitrogen, oxygen, and fluorine, okay? Acidity goes left to right. What's the reason? Why is HF stronger acid than methane? Oops. Electronegativity. So if I put all the hydrogens here, fluorine is a lot more electronegative. It's going to pull electrons in this direction. Okay? That means you're going to have a great polarization in that bond. Great separation of charge. Fluorine is a big delta minus. Hydrogen is a big delta plus. So you can easily remove it. So it's electronegativity. Down the group, Hi is stronger than HF. What's the reason? Size. Iodine is a huge atom. Hydrogen is the tiniest atom on the periodic table. Overlap between hydrogen and iodine is very poor, very weak. Bond is very weak. You can break it easily and you can knock out that hydrogen. Okay? So you have to drill this electronegativity across down a group. It's a size effect. So that one, yes please.
So acidic is more reactive?
No, you have to be careful. Acidic is more reactive in an acid-based reaction. Because I don't want you to get me in October and say you said something. Because the theory changes. I wouldn't generalize it. I'll say if it's more acidic, yeah, it's more reactive in an acid-based reaction. So in a different reaction, HF may be just sitting around doing nothing. And CH4 may jump and react. Depends on what kind of reaction. Okay. So inductive effects, that's our second one. So let's look at that. We have a couple things there. One is more acidic than the other. So we want to know why. The most polar bond is right here. So what this means is I can get a base. This is a fast reaction. I can get a base. This is a slow reaction. Why? So the base is not going to be so fond of grabbing that proton in molecule 1, but it'll be a really fast reaction in 2. Obviously, the difference in both is the fluorine atoms. So what do you know about fluorine? There's only one concept I associate with fluorine. It's the most electronegative element. It's going to be pulling electrons. It's not just pulling electrons in this bond to carbon. It's going to pull all the electrons in the molecule towards it. Okay? There's a difference between electronegativity and inductive effect. Electronegativity is something like this. Fluorine is very fond of these two electrons. Okay? Inductive effect is, I got a fluorine somewhere in the molecule. This guy is fond of all the electrons. It's pulling it from different parts of the molecule. It's an extended electronegativity effect. Okay? So these three fluorines say, yeah, I'm going to pull all the electrons in the bond I share with carbon, but I'm also going to pull all the electrons away from everywhere else. What that does is causes great polarization in that oxygen-hydrogen bond. What I mean by polarization is greater unsymmetrical distribution of electrons. So you can knock out that proton more easily. Okay? You have a big delta plus sitting on that hydrogen, the second molecule. This is called inductive effect. Inductive effect is an effect because of electron withdrawing groups. It can also be because of electron donating groups, but as of today, we'll stick with electron withdrawing. We'll introduce the other one later. Okay? Next is resonance. One more acidic than the other, which means the base wants to come and grab this really fast, but the other one not so fast. So if you think back about Gen Chem, acid-base is an equilibrium concept, right? So something is a really good acid if it forms a whole lot of conjugate base at equilibrium. So I wanted you to write the conjugate bases that you get out of these two. So let's write the conjugate base that you get from the first one with the correct charge. That's what I get from the first one. The second one, let's write that. I'm going to open this up. So the right side molecule is more acidic than the left side. So which conjugate base is more stable? 1 or 2? Which one is more stable? 2. Now you're going to explain why 2 is more stable than 1. It's what we studied last week. That concept comes from last week. The word begins with R. Resonance. Can you draw a resonance structure for 2? So go ahead and draw it. You must draw it. It's there. So that is the reason. It's resonance stabilized. So you want to draw that structure. How do you draw a resonance structure for 2? Very good. Move the lone pair to oxygen. So I'm out of space. I'm sorry. It's getting a little clumsy, but we're going to move a lone pair right here. We're going to put the lone pairs on that oxygen, move it right here. So we get a second resonance structure separated by double-headed arrow. You cannot draw such a structure for 1. Those lone pairs are not going to move towards carbons, okay? Electrons love to move. They don't want to stay stationary. Charges do not stay stationary. They like to move. So when you sit in the same place, you're not doing much work. If you move from place to place, you're doing work. So I want to think 2 pictures of you. You sit in the same place all day doing no work. You have a lot of stored potential energy. You get up and walk around, go to the gym, you do whatever. You're doing a whole lot of work. Your energy drops. You are spending energy, okay? So in chemistry, less energy means, what is your comment on stability? Lower the energy, more stable, right? That's how it goes. That's the very premise of our science. Low energy, high stability. So 1 or 2, 2 is more stable. Why? Because it is resonance stabilized. If your question is, what is resonance doing to stabilize it? It's moving the negative charge. Can you see that? So the electrons are moving. They're doing a whole lot of work, moving from one place to another. So their energy drops. Lower the energy, more stable. Okay? Every time you move the electrons from point A to point B to point C, you're making it do work. It's dropping its energy. Lower energy is more stable. So 2 is more stable than 1. Why? 2 is more resonance stabilized. That's enough for a chemist. You don't have to explain how it's doing a lot of work, it's spending a lot of energy. All of that is contained in those two words, resonance stabilization. That's what you mean. That's what you mean, okay? I'm just going into a very verbose explanation, but that's what it is. Okay, let me take a quick look at the time. I got some time. So let's go to 4. Any questions on 3? Yes.
The setting, the number 2 structure near the more acidic. What is that for the COO structure?
Yes, I've expanded it out. Without
Okay.
expanding it out, I don't think we could have drawn a resonance. So I expanded it out and drew the Lewis structure.
Okay, so the original structure is more stable than resonance structures?
No, what I did was I got the base to grab the proton. I jumped a step, and that puts the O minus right there. So what you get out of that looks like this. But this I didn't think would be a good structure to show resonance. So I opened this structure up to draw this one. Am I answering your question? So I won't say, if you're comparing this structure with this, no. That one, the base came and grabbed the proton and formed the conjugate base.
Well, under more acidic it says more stable, so I'm just wondering about that comment.
Okay, this is more acidic, but the conjugate base is more stable. 2 is more stable than 1.
Okay.
So you have 2 conjugate bases, 1 and 2. 2 is more stable than 1.
Okay.
If 2 is the product that you get from the acid. The product is more stable than the storing material. The reaction is going to go faster. Okay. Anything else on that? Okay, last one there is a hybridization effect. So I have written a whole bunch of things there. So we have these. This is a double bond, so I'll rewrite it. And then you have the triple bond. Okay, so we have sp3, sp2, and sp. So we're talking about removing this hydrogen, these hydrogens right here, and these hydrogens right here. So if a base came and attacked, it's going to attack this hydrogen really fast. Okay, so the question here is, you can remove a hydrogen connected to an sp carbon way faster than you can remove the one connected to sp3. So the question is why? It's a hybridization effect. sp3, sp2, sp. So which is the more electronegative carbon? Correct answer is sp. Why? Which one has greater percent S character? sp. What's the percent S character in sp? 50. Why am I making a big deal about the percent S character? It's closest to the nucleus. S orbital is the closest orbital to the nucleus. So in an sp hybridized carbon, you have 50% S character, which means it's going to look 50% like S, compared to sp2, which only looks 33%, sp3, which only looks 25% like S. Okay, so an sp orbital is the closest to the nucleus. So the nucleus is going to pull the electrons towards it. That carbon is really electronegative, which makes that bond really polar, and you can knock out that hydrogen. So alkynes, triple bonded compounds, you got the functional group today. Alkynes are acidic. Alkanes are not acidic. Alkanes are neutral. Alkynes are acidic. Alkenes right in the middle. Okay. That's a really important slide. As I said, the next several slides are going to be problems. So I have 3 minutes. Maybe we can hit this one. Maybe. If not, we will start back here. But you're going to explain the pKa differences below. So each problem will test you back on the concepts you learned on the previous slide. So we have 4 acids. The pKas are given. Keep in mind, you may not be given the pKas on the exam. Okay, but given the pKas, let's go ahead and explain. Which is the strongest acid? So you're going to explain why 0.7, that particular acid is the strongest one, and 4.75 is the weakest. So you have 3 halogens, all right? That much is clear. They're not fluorines, but they're chlorines. The big picture here is inductive effect. Okay, so if you're going to call this 1, 2, I'll usually label it so you can use the labels. 4 contains 3 halogen atoms which are very electronegative. It's going to exert a strong inductive effect. That is the reason. Okay, you don't have to explain what inductive effect means, but do you know what that is? In your mind, you got to know what you're talking about. Inductive effect means, yes, they're going to pull the electrons towards them in that bond, but they're also going to pull the electrons from everywhere in the molecule towards them, okay, which makes this bond very polar. And therefore, the base can grab that proton more easily. You don't have any halogen here. So it's absence of inductive effect. So you don't have to explain what inductive effect is, but you have to bring that term into your explanation. You're going to say acid number 4 has 3 halogens, exerts the greatest inductive effect, makes it the strongest acid. Okay, that's good enough. So we will stop here because we are right on time. And then we'll continue. All we're getting is a whole bunch of problems. We'll work that out. And then we'll build on that. Okay, more. So I think we are doing well with time for our exam. I'll keep you posted on that. So Wednesday section, lab section, I won't keep you for too long, but you may have to show up for a couple.